I expected different thing.
Yeah. Hey, well, too loud, I guess. Is this fine?
Yeah.
Perfect. Just before we start, I assume English is the preferred language, right? So if you are strongly opposed to it, raise your hand or stay silent until the end. Okay. So this is the 10th C++ plus systems meetup in Armenia. It's our anniversary. And we wanted to do something systems oriented because the last few meetups were more about C++. So we thought Linux is the perfect topic because it's in every server, it's in the cloud, it's in mobile devices, especially on Android. But before we start, I just want to mention that this time we also have a microphone. We'll start with a talk that will be roughly 30 minutes. We'll have a Q&A session after that one, and then we'll have the second talk by Dmitry Duka, which will also be on the topic of Linux and the intersection of Linux and GPUs in a very weird way. So time to get excited. I'm quite excited for this one because before this, I think I've only talked about this in Armenia once at AMD office here a couple of years ago, and some of the material aged well, the rest didn't. So the topic for today, for me, is how to make the databases and web servers 10 times faster on Linux specifically. So Linus Torvalds is the benevolent dictator of the Linux ecosystem. Almost every major open source project has its dictator, and I think the world is better for it. He's known for a few very catchy phrases. I hope AVX 512 dies a painful death. That's quite well known in the high performance computing community. I totally disagree with this one. I think AVX 512 is probably the best instruction set we have right now. Software is like sex, it's better when it's free. Also true. Talk is shit, show me the code. That's beautiful, but we'll not have too much code this time because the topic is too deep. And any program is only as good as it's beautiful. Oh, sorry, as it's useful. I'm not sure I agree with this one. So I kind of like elegant code, even if it's not working or if it has bugs. But then there's like one code that I'm almost sure I've heard him saying that, but I couldn't find it preparing for this talk. And I think at some point he said like database code is tasteless, and if he indeed said that, I would add database code is not just tasteless, but it's also mostly slow. So compared to what modern hardware is capable of doing, modern database and web software is very far behind. So 2-3 years ago, like almost every year actually, I prepared an article about the upcoming wave of hardware. And the reason for this is that when you implement something in hardware, you can squeeze like 10 times more performance out of it. Everyone who is remotely familiar with things like crypto knows that at start we used CPUs for crypto mining, then we did GPUs, and then we switched to ASICs because when you program the logic in hardware and use a comparable lithographic node or lithographic process, you actually squeeze a lot more performance from implementing that entire logic in hardware. So when hardware gets support for some new interesting features, you better use them. Otherwise, you're paying for hardware you're not using. And you can actually literally see that on silicon. So you take die, you map out the regions and what they're responsible for, and you realize that conventional cores on modern CPUs do not make up 100% of its surface area. There are a lot of other specialized regions that we don't really use properly. So for today, for the servers that I work with, most servers have over 100 cores per socket. On x86, oftentimes they would be hyper-threaded, meaning you have 2 logical threads of execution on a single hardware core. One thing that wasn't true even a year ago, I would say, we didn't really have broad SVE support. SVE stands for Scalable Vector Extensions. Those are the specialized vector extensions of the ARM instruction set available on 64-bit ARM, available on modern servers CPUs. And examples of those would be Graviton chips. So most of you know what AWS is, right? Raise your hand. Perfect. For others who don't or are too lazy, it's a cloud business with over $80 billion of annual revenue. And because they're so big, they have to be efficient, so they build their own chips based on ARM, and they had 4 generations of those chips. Third one, the one they released last year, already had support for SVE, and the new one has support for SVE2 on Graviton 4. And what SVE is special for is like this vector extension that, unlike any other instructions or registers available in modern computers, at compile time you don't really know the size of the register. So when you use modern compilers and you write conventional code, all of this code is compiled into a binary that works with fixed size registers. You have 64-bit registers for integers, 32-bit registers for integers, you have some floating point units, those can be different sizes, you have SIMD registers, on x86 they can be 128-bit for SSE, 256 bits for AVX, 512 bits for AVX 512. For SVE, you don't really know. For SVE, you have your code that works on high-level register wrappers or something like that, and when you compile the code, and then you distribute it to different machines, you may end up running on a machine on which the SVE implementation is either 128 bits, 256, 512, 1024, or 2048. So with this, you may already see that the hardware today on the CPU side is becoming more and more similar to GPUs. So the CPUs now have registers that have thousands of bits in width, and you have hundreds of cores, very similar to GPUs, I would say. Another thing that was long overdue is the widespread adoption of AVX 512. So AVX 512 is kind of available since 2015, depending on how you count. It's available with Skylake X CPUs on the Intel side, and everything newer that came after this. So AVX 512 instructions, they would work on 512-bit words, and the most magical thing about the fact that it works on 512 bits is, at this point, it would be actually cool if someone shouts why 512-bit words are cool. Any ideas? Don't be afraid to be wrong. Yeah, so the register size is like 512, but why is it so cool?
You can actually store many data on that 512-bit register and perform some operations.
That's kind of true. Bigger registers means you can kind of deal with more data at once, but it also generally means like higher energy consumption. So just like going to extremes and having like megabyte size registers wouldn't be a great idea. But the reason 512 bits are so amazing is because it matches the cache line size. So the memory system of the computer is already kind of built to work with this size of words, that all of the levels of cache associativity, all the associated containers in the hardware are kind of designed to handle this size very well. And in practice, I have a project called Stringzilla that really benefited from this fact. Another fact is that DDR5 is now broadly available on the server side, HBM as well. HBM is the high bandwidth memory. Historically, you could find HBM only on the GPUs. Starting with Intel Sapphire Rapids, you can now get CPUs with high bandwidth memory on package. It sounded like an absolutely amazing idea when I first heard about it 3-4 years ago. But in reality, it turned out to be not so great. So on the GPU side, high bandwidth practical utilization is 2 or 3 terabytes per second. On the CPU, it's still hard to get over 500, 600 gigabytes per second. But even with DDR5, we can often get over 300, 400 gigabytes per second per socket. So a lot more memory throughput. Latencies are not getting better, but the throughput is rising. So again, we're getting closer and closer to GPUs on the CPU side. But then the GPUs are getting better, the SmartNICs are getting better. So with all of this today, we probably should think about how we change the approach we write software. One thing that was always on the radar, at least for the last few years, was CXL, which is the new protocol for cache coherent memory extensions and all kind of external devices. I would say it's still a bit far off. Another thing that is kind of important, but I don't think we've done enough progress on this, is managing unified memory. So most of the modern CPUs, GPUs, and APUs have some form of functionality for you to allow allocating memory in some shared pool, and then it would transparently allow you to access this memory from different devices within the same server. Or with RDMA, remote direct memory access, you can even access them from remote servers. So all of the current hardware used for large-scale AI pre-training, like DGX H100 nodes, is kind of designed with this kind of capability in mind, being able to do RDMA, being able to access unified memory, but the transparent approach for handling this is not great. Transparent meaning that you just say this memory is unified, and then you just assume that the driver does all the heavy lifting, kind of moving the memory from one place to another. Manual approach, I believe, is still the best. And then there are like a few topics like APU kernel scheduling and others that I haven't mentioned on the slide that are relevant, but the most important one for today is Linux kernel bypass. So Linux, being the default operating system for servers for the last few years, has added a lot of functionality to make working with this fast new devices like SSDs and smart NICs really fast. And it kind of focused on two things, asynchrony and system calls. So asynchrony is a concept very well known to programmers across every programming language, starting from super high level things like JavaScript and Python, ending with low level languages. But of course the implementation of asynchrony is different in every place. So most of the code that I saw using asynchrony in Python and JavaScript honestly sucks. They would use asynchronous functionality, which under the hood would invoke task schedulers, load balancers, promises, heap allocations, atomic variables, all of that crap to kind of implement a very niche, small, granular workload. It's like calling a server on a different continent to sum two numbers. You don't need to do that if you only have like a very small workload. Then there's system calls. They're kind of different from the concept of asynchrony, but those are very tightly related. So system calls is the procedure of your application calling into the operating system to perform something that requires authorization. So those can be different operations. One of the operations that involves system calls from time to time is memory allocations. When your program starts, your default memory allocator will allocate a few arenas. It will allocate an address range for them from the operating system. So operating system is involved into the bookkeeping process. It knows which process on the machine uses which part of the address range. When you allocate a lot of memory, at some point the memory that is available to your memory allocator is already used up. So it needs to go to the system, to the operating system, and request more. And those operations, when you request the operating system to do something, they have non-deterministic complexity, or I should say latency. So depending on every single condition possible, starting from CPU utilization in that specific second, or weather on Mars, the latency of a specific operation, like memory allocation, can be very, very different. In our specific context, the system call that you notice most often when you read and when you work with databases and web servers is reads and writes. So when you have a file somewhere on disk, you open that file using a system call, by the way. You get a file descriptor, which is generally on Linux 32-bit integer, and that file descriptor is how you address the files within your file system. Then you tell your computer you want to read some data from that file, addressed with a file descriptor again, or you want to read some data back into that file. Historically, we had several ways to do that. There is a family of operating systems and standards called POSIX. Some people often assume that's the same as Unix, but not entirely. So within POSIX API, there are two function calls, pread and prewrite, which will allow you to read and write the data given the file descriptor. Everyone who studied C or C++ has used pread and prewrite at least once. Sometimes you do that through libc, so you would just like get not the file descriptor, but a file opaque pointer, and that opaque pointer later will be used in conjunction with libc's read and write functions, which in turn will unpack the opaque pointer, will get the file descriptor integer, and will call pread and prewrite. So every time you call into libc on Linux, you end up with those pread and prewrite calls, with some layers of buffering on top. The second approach that database developers surprisingly love is called memory mapping. It's the easiest way to read and write data from disk, especially if your file size doesn't change. So essentially, what you request the operating system to do is to map an entire file into a range of addresses in your computer's memory, and then you access those bytes as if they are in memory. But that's not really magic. Like, there is always some latency involved, there's something that's happening in the background. So whenever you access a file, like a pointer that in reality maps to somewhere on disk, you end up with a blocking operation, again, very similar to pread and prewrite, that will fetch that page of data from disk, will put it into memory, and sometimes using memory mapping, you end up with performance that's lower than pread and prewrite. It's assumed to work like magic, but it's not. So at some point, actually like very long ago, as early 2000s, I think it was 2001 or 2003, at that time I wasn't doing database development, there was an interface called AIO added to Linux. A in AIO stands for asynchronous, IO stands for input and output, as usual. And then there is like a counterpart, I would say, that is semantically similar but is designed for networking called ePOL. ePOL is widely used, AIO is widely used, but those concepts and like those interfaces are still over 20 years old at this point. The hardware has gone far ahead. So in late 2010s, there was a new effort started by Jens Axbo, who's one of the core maintainers of Linux, to introduce a new interface for asynchronous I/O called IO-URANG, which can be used for both storage and networking. Now it's broadly available. It's used by some more performance-oriented database and networking vendors. It's also not state-of-the-art, but it's the one thing that we'll focus on for today. But then there are like more advanced solutions. So like, at least worth mentioning, there is like a family of user space drivers. I would say Intel is the biggest backer of those projects. SPDK, I assume standing for Storage Performance Development Kit, and DPDK, I assume stands for Data Performance Development Kit. Mostly designed for applications like NVMe over Fabric, or very high throughput and low latency storage and networking handling. NVMe OF stands for non-volatile memory over Fabric, and Fabric is generally infinite. And then, assuming we deal with a lot of GPUs, FPGAs, and all kinds of other accelerators, it's assumed that at some point GPU vendors would jump into the race and implement something designed for GPUs. And for that, we have GPU Direct Storage, which I assume has changed name 3 times in the last 5 years. So I'm not sure GPU Direct Storage is the name we refer to today. But in essence, it's the approach of sending the data from the disk, or not really a spinning disk, but NVMe device into GPU memory bypassing the CPU. So a very good solution if you need to, if you need to send a lot of data, but again, talking about IO today. We have a question.
What about VDSO?
Okay, VDSO has some applications. I'm not sure it fits on the same page. So VDSO can be used for lightweight system calls. I'm not sure it can be used extensively and well for storage, but I may be wrong. Good question though. So the question might be like, why systems call matter so much? I assume if you've ever done like performance optimizations, one of the first things you do, you remove memory allocations. So on a hot path of your code, you don't want to call malloc. You don't want to call the std allocator. You want to avoid that. Again, because it's non-deterministic latency, but even if it is not requesting anything from the operating system, most modern memory allocators are really complicated tree-like structures. most of the time it's some form of trees of linked lists that are also linked between each other, really messy, a lot of pointer arithmetic and not the pretty kind. And even without like those system calls, just the traversal of those trees oftentimes takes 50 to 80 nanoseconds at least, which is comparable to the cost of very lightweight system calls. So get aux-val, get time of day, get UID can be some of those examples, get process ID. So even the most lightweight system calls would also have a latency of at least 50 nanoseconds. The more expensive ones, if you're lucky, can be in order of hundreds of nanoseconds, but in reality, much more. By the way, like I assume get UID and get CppID are the most common system calls replaced by VDSO, at least from what I've seen. Oops. That's interesting. Okay, weird. So theoretic measurements of like individual system calls never tell the whole picture. Like we're talking about databases here. And one of the most interesting lines of work that I was doing here in Armenia a few years ago was working on a database engine that would benefit from some of those tools like IOUring. And at the time, even with the hardware available back then, we registered a 7 times performance improvement in mixed workloads, in batch reads, in batch writes, in branch selects. So almost all critical operations that the database engine would do would be accelerated by a factor of 5 to 10. Can be a bigger difference today. And assuming those are very low-level database operations, you can imagine that every database that doesn't use this is most likely at least 5 to 10 times slower than the hardware allows. In reality, 5 to 10x performance difference from the hardware potential is somewhat generous. In reality, when you disassemble databases like Postgres or something like that, you realize that in theory, if you like map and read out all of the memory, organize it in arrays, structures of arrays, as opposed to arrays of structures, use vectorized code on top of them, modern CPUs are pretty good at crunching tens of gigabytes per second on one core, or handling hundreds of gigabytes per second across the cores. But in reality, all of this very slow synchronous I/O down there on the disk is only yielding 100 megabytes per second in mixed workloads, sometimes less than that. So in this specific case, between 100 megabytes per second and 100 gigabytes per second, we're talking about 3 orders of magnitude performance difference accumulated across all of those layers, such as the object relational mapping, the query engine, ETL, and the rest. So that was actually one of the reasons why I believe systemic approach is needed to update more infrastructure. You cannot just design a new key value store or a new web protocol and its implementation. You actually have to go through all of the layers, including the database engine, including the ETL, including the object relational mapping. And doing it with IOUring requires understanding of a couple of very basic concepts that are common for almost every driver implementation within Linux. So most of the time, when you think about Linux, you think about like this ring-like structure, where at the core is the kernel, and there are like different security level dependent rings. So at every ring, the software has different privileges. User space code is the least privileged one. Kernel space is the most privileged. And for them to collaborate to, let's say, read or write data, what happens with IOUring is you allocate memory and you put a couple of queues in that range of memory. So if you allocate memory using like map shared flags or something like that, you already know that that same memory buffer can be reused between different processes. So let's say you're working with a very large file and you're doing it in Python, not even C++. And you have like different threads or different processes that try to access the same file, and you don't want to get too messy with IOUing, you just use memory mapping. If you allocate and like map that memory buffer using map shared flag, it would already be very helpful because different processes will reuse the same cache for those memory pages. In IOUing, this map shared is used for a different thing. The processes that are communicating are not both in user space. Those are not processes exclusive to your application. One of the processes will be on the kernel side and the other will be on the user side. On the user side, you submit operations. Like instead of saying pread and blocking, you say, I want to read some bytes from this part of memory. You submit this operation into the queue that is in the shared memory buffer, and then you go do your other tasks. In the background, the kernel fetches those new submitted operations from the submission queue, here on the left on the second picture, executes them in the background, and when the time comes and when the data is already available, the second ring buffer, called the completion queue, gets the notification that the operation is done. And there are a couple of mechanisms on how you can work with this. Most often you would be polling the second queue, checking if there is something available. This kind of chart and this kind of graphs you can find maybe on 5-10 blogs on internet, so it's a common knowledge. Something that is less common is practical experience of knowing how much performance you're getting from what kind of hardware. On the Samsung enterprise drives that we use or used at the time, our mixed workload benchmark suggested that synchronous calls with POSIX, like everyone does, like libc does it, would easily bottleneck at 100,000 operations per second. Assuming your disk is capable of 1.5 million operations per second, if those are similar drives to ours, you could easily unleash 15 times more throughput. Well, okay, not easily, but you could. AIO, which is available for over 20 years now, allowed us to squeeze 250,000 operations per second from one SSD and one CPU core. It actually doesn't really scale well with more CPU cores because synchronization is expensive. Using IOUing with one SSD and one or two CPU cores, depending on the CPU model, we can get as high of a number as 900,000 operations per second. With SPDK, which was at the time the state-of-the-art user space driver approach, we got to 1.2 million operations per second, which is over 80% of theoretical throughput of the drive. Not too bad if you're measuring the end throughput of a database. Being at 80% hardware utilization is practically state-of-the-art even for things like matrix multiplications that do not require this much of complex scheduling between different devices in the same machine. Those same results that are available for storage systems are also available for networking. A couple of years ago, I had a couple of free days and I wrote a library called ucall. And the reason I wrote it was I was sitting here in Yerevan and I drafted some AI application, whatever, in Python. And in Python, the go-to server library is called FastAPI, server backend library. With FastAPI, you can use a couple of decorators in Python to kind of announce a web server and serve some traffic, serve some web pages, implement RPC, whatever you want. And it's widely popular, yet it's not as performant. So fast in FastAPI doesn't really stand for throughput, it stands for implementation ease. So it's really fast to get it working, but once it's working, it's not really fast. An oxymoron of a kind. So the REST API that I implemented had the latency of 1.2 milliseconds on the server and 6 milliseconds on the laptop with Core i9 CPU. So that's the latency comparable to a signal traveling from Armenia to Georgia. 6 milliseconds is a lot. When it's two processes communicating on the same machine, that's too much. So I knew something is off, and I rewrote FastAPI and actually implemented something similar to it in IOUing, and it ended up being one of my most upvoted posts on Hacker News, getting to 70 times the throughput of FastAPI with 50 times lower latency with implementation that is only a few thousand lines of C99. That was quite nice. I'm pretty sure I'll release a new version of this that is production ready later this year. So I'm not even using this myself because it's not mature enough. But it turned out that there are some Fortune 500 companies that rely on the development branch of this, which is weird. But I guess some people need performance really badly. Yes?
Yeah, while we are fixing this, the last number, 231,000 requests per second, is it single core or multi-core?
It's single core server, and it's 230,000 RPS, and RPS is measured as a ping and a pong. So I aggregate from all the clients, and every client cannot submit more requests until it receives the answer of the previous one. So this number is actually my lower bound. Last year, or like this year, I was gathering in San Francisco with a lot of like kernel developers, including like part of the Linux core maintainers, and they tested like one of my prototypes, and we realized that in reality my throughput is 8 times higher. So depending on how you write the benchmark, the gap can be more significant. So one of the guys who was like benchmarking with me, independent from me, he suggested that the real throughput is 1.6 million operations per second. But I have to repeat before I can claim this number. So until here, it's old news. Here where true state of the art begins. 2023, 2024, after I released the original prototype of U called the networking library, a few things were implemented in IOURang, but you cannot always get access to them. It depends on the version of your Linux kernel. So it's a very, very good practice to stay on the bleeding edge of the most recent compilers, and I would say the most recent Linux versions. So Ubuntu 24.04 long-term support version came with kernel 6.8. And it had a bunch of features in IOURang that were not available when I was prototyping the ucall, because at the time of prototyping ucall, the newest kernel was 5.19. So it's even a different major version. In 24.10, it's expected that 6.11 would be the kernel. I haven't checked if it's the case. And we got a few nice things in those recent releases. The first one is that you can bundle multiple send and receive calls. This is not exactly what it sounds like. Another thing that is absolutely amazing is there is now a fast zero copy path for small packets. So when you exchange data over the network, most packets are actually quite small. There is this notion of MTU, maximum transmission unit, the upper bound on the size of individual packets. So whenever you're sending even really large files, like a few gigabytes in size, across the internet, they will be split into those MTU, maximum transmission units, depending on the underlying protocol. Like on the TCP stack, it will be one thing. If you're using UDP, it's a different thing. So for packets that are under 3,000 bytes, which is larger than MTU for most protocols, there will be a super fast zero copy path within IOURang. So the 1.6 million can become even better. And then the new cool thing in Linux kernel 6.12 is absolute timeouts. So what it means is that when you build up your finite state machine of your networking backend, you end up with different operations that are interconnected. So you cannot start receiving on a socket before the socket is open, right? So we already have like a state transition. We first open the socket, then we start listening, then we receive the message, we parse it, then we are ready to listen again and receive the next part, the next packet. This is a state machine. And within the state machine, one of the most common operation is defining timeouts. Like you are not really waiting for the next message anymore if an hour has passed or 2 hours have passed. So it's a lot of time, of course, but the same is true for shorter periods, like a few milliseconds or a few seconds. In newer versions of IOURang, we now have this absolute timeouts, which are absolutely amazing, but I may not even be able to use them these days. If the question is, okay, Ash, what's the problem? Just install a new version of Linux kernel, just maybe switch from Ubuntu to Arch. It's not that easy. You either have to have bare metal access to the machine to be able to do all of those things properly, or you have to wait for cloud vendors to adopt newer kernels. So the newest kernels that are available on AWS these days, they have Linux 2404. So I cannot use absolute timeouts today. I cannot bundle send and receive calls because it's 6.11, and AWS only has the Ubuntu 2404. So already at this stage, we see that there's a lot of mixing and matching of different functionality. If you use period and pwrite, that's available for 40 years now, yes, every cloud vendor, every software has support for it, but if you're on the bleeding edge, your source code is full of switch statements and ifs, being able to, that are required for you to check if the hardware supports and the software supports what you're intending to do. What's relevant to understand about IO-Uring, its advances are interdependent on kernel updates. So even if the Linux kernel, even if IO-Uring is receiving some functionality, and you're reading the updates and you may think that that's it, like the first 3 bullet points, in reality, it's important to check the update notes for the Linux kernel itself, because if the Linux kernel gets better support for zone devices, or something like that, then all of the operations on top of IO-Uring for storage will also inherently become faster. And it's kind of this hierarchy of software that's interdependent and built upon each other. So IO-Uring is kind of our better interface into Linux kernel, but we need to understand how Linux kernel works. To give you a little bit of intro on like where to look and what to do with IO-Uring, I think one of the most important features that is missing in my prototype is multi-shot requests. So when you send a packet through network, it may just so happen, or like you send a message through network, and it may happen that you're expecting multiple messages in return. For that, there is now a multi-shot capability, and it's been around 6 version of the kernel 6.0, and there are man pages like the Linux manual with documentation for this, and the function signatures on the left side. On the right side is what we now get in 6.11, for example, the bundled sends. And if I were to read bundled sends, I would assume that we're getting not a submission queue entry, which is the SQE over here, not a pointer to it, but a pointer to pointer. So I would assume bundled calls means I can put multiple queries like this together and pass an array of those bundled queries. But now, in reality, the way this works, you just have an internal member variable inside of this that helps you notify the kernel which pool of buffers you can use, and if multiple calls use the same pre-registered buffer, then IO-Uring will work faster. I don't expect you to understand what I just said, because it took me an hour to build up a mental model for this. And I've used IO-Uring before. So what I'm trying to say here is that IO-Uring may not be too hard to get started, but it's clearly much, much harder than using period and pwrite. And if you want to build up a project that uses all of this, I suggest you allocate enough time, ideally a couple of weeks, and dive into the documentation. Moreover, the documentation is fragmented. Part of the documentation is available on the Linux manual pages. Part of the documentation is available on the IO-Uring website, or like liburing website, and part of it is on GitHub. But honestly, none of them are complete, so you should go to the source code. That's not ideal, I understand, but the ground truth is always the source code, and liburing is not that long of an implementation not to read. Another interesting thing that is true not just for IO-Uring, and I want all of you to remember this. Even if you don't use IO-Uring, there is this flag called oDirect. If you have a place in your program that reads or writes from disk, and you want to do something tonight, once you listen to all of those talks, go home, and whenever you will try to open a file and read from it, try adding one more flag, oDirect. First, your program will break, most likely. Because oDirect means you cannot really use libc's caching layers to read the data in incremental fashion, in small or large buffers, whatever. oDirect means you're on your own. But if you can avoid and bypass libc's caching, you're not paying for those extra abstractions. And C++ people, they don't like paying for abstractions. I'll be the first one to condemn abstractions. So if you add ODirect, you will be forced to read the file in a very specific way, but doing it just once will help you understand how SSDs work, how networking works. It will also make your application a lot faster. So definitely must try. And in 6.12, in IURing, there is now a feature that allows you to work with ODirect buffers in a slightly more advanced fashion, but this might be too much for a first week of prototyping with IURing. Still, the slides are here. They will be on the GitHub page of the C++ Armenia community, so go check them out. And the reference link is below. I also mentioned something related to the Linux kernel itself. Like, your application is not just dependent on what kind of IURing functionality you're using, it also depends on some other hardware offload functionality that is available to Linux applications. Probably the most attractive feature I don't get to use enough is KTLS. It's a feature that allows you to offload the cryptographic or like encryption stack relevant for TLS, transport layer security, which is kind of part of the modern web stack, onto the networking card itself. So if you're using one of the new fancy high-end networking cards, or if your software runs in a data center that supports this, as early as with kernel 5.3, which is quite old, you can already benefit from KTLS. And cryptographic part of the web stack is, I would say, not just by far the most expensive part of the stack if you're using a high-end encryption standard, but it's also by far the ugliest. When we were working on UCall, we allocated many, many hours, I would say even months of engineering time, to compare OpenSSL, Boring SSL, which is Google's fork, and maybe like Embed TLS, maybe 3-4 other vendors. All of them were bad in terms of implementation and horrible in terms of interfaces. So it's hard to combine an existing TLS implementation with a new kernel bypass thing, for example. So like if you use OpenSSL, OpenSSL thinks that you are a vanilla developer. OpenSSL doesn't believe in you like I do. OpenSSL says, whatever networking operation you're trying to do, whatever kind of networking stuff is on your mind, just give me the packet and I will call pread and prewrite for you, adding encryption on top of it. But then one day I come in and I say OpenSSL, guys, I don't want to do pread and prewrite. We're too high-end for that. We want to do DPDK, we want to do IURing, we want all the bells and whistles, and OpenSSL will not allow you to like take only the encryption part and then add your transport part, or IO part. Maybe last really fancy thing that I would just put here is CXL. CXL has been part of my wish list for a few years now. And if you look at the date on the article, September 24 is like practically the first SDK ever published. So it's like very recent news, but like I've been trying and waiting for this thing for 4 or 5 years now, maybe. CXL allows us to connect devices within high-end servers in a different fashion. So it differentiates 3-4 different kinds of devices. Among them, the most important kind for most developers will be coherent memory. So essentially, when you build up a server, you have a CPU and you have multiple channels of RAM next to it. And RAM chips go into DIMM or SO-DIMM slots. But then we also have PCIe slots where we generally put GPUs, right? And then we also have M.2 slots, which are also PCIe for SSDs. That's in the consumer grade hardware. But what if we could reuse PCIe connections for different kinds of devices, such as memory? What if we do not really install RAM sticks into SO-DIMM? What if we install RAM in the same place where GPUs go? That's potentially fun if you really enjoy hardware and like putting weird things in weird places, but it also has a practical application. So potential value of this is being able to extend our systems with many different kinds of memory with different latencies and throughput. So example can be having a high-end server with DDR5 memory or HBM, who knows? And like HBM package and DDR5 in SOTIMs, and then using this TXL to buy a lot of very, very cheap DDR3 and DDR4, which is like several times cheaper than DDR5, assemble them into large memory pools, and install them next to GPUs, somewhere there. And with this in mind, I guess today we're limited to maybe 6 terabytes of RAM per socket, which is of course a lot more than most people experience, but you can get 6 terabytes per socket these days. But with CXL, you can actually go far beyond this. Who knows, maybe we can put like 50 terabytes, 100 terabytes of RAM per socket, and in that case we can really work with internet scale data sets in memory without ever having to touch disk. This will change databases a lot. To just give you a brief insight why I think C and C++ developers are really well positioned to win in this war for advanced hardware, and why I believe Rust is not the ideal choice. This is a snippet from one of my libraries. When you need to implement hardware-specific features, you need to know what features the hardware supports. As trivial as that. And even when you do that, there is no built-in, easy way in compilers to check if specific functionality is supported or not if you're at the bleeding edge. To give you a perspective, like last week I was adding feature flags into LLVM to detect the CPUs that haven't come out yet. But we need to be ready with our packages. So on the left is a snippet from a production library that runs on over 100 million devices that uses inline assembly, not even C or C++, to detect CPU features on x86. And you have to do it differently on ARM, of course, because the assembly is different. Because MSVC, one of the default compilers, doesn't support inline assembly, unlike GCC and Clang, you have to use some weird intrinsics, which is horrifying. And then on the right is the part that comes after this. So you take the CPU feature registers like the info register 1, 7, and register 7 leaf 1. If that tells you anything amazing, call me afterwards. And then we use 4 different words, EIX, EBX, ECX, and EDX, also matching the names on x86 to understand if a specific flag or a specific beat in those words is set, then the CPU supports this specific instruction. And the instructions can be very weird. There can be like a specific check to say that on x86, for example with this one, AVX512BF16, means that if you have 2 AVX512 registers, so 512 bits, there is a dot product instruction for BF16 words, which will take nearby BF12 values, multiply them with F32 precision, accumulate neighboring values, and add to the third register. So those features are impossible for compiler to use. So like if you write C++, compiler will never know that it has to use these features. So you have to code assembly directly or use C intrinsics if the compiler supports that. But you also have to check if in the specific distribution of your library on a specific machine, you can use this instruction. And just the checks alone can be thousands of lines of code. So this is not kernels. This is a part of code from one of my libraries that is just a lookup table to say on which CPU, which kernel implementation to use. And I didn't want to shock you too much, but there are a few more slides like this, so I decided to remove them. As you can imagine, there's a lot of boilerplate, but I'll soon publish an article why this is the only way. Still, there is some hope, and hope comes from enthusiasts like us, the ones who end up writing all of those kernels so that the rest of the community can benefit. This day, I mostly work on those 4 libraries. Some of them work on over 100 million devices. All of them are open source under Apache 2 license, so if you have like some commercial product you're building, you can easily use them there. I would say that they're pretty good for educational purposes, so all of them have long readmes, long documentation. Also on GitHub issues, I always try to mark issues that are good for first-time contributors. So if you open up the issues for those projects, you can see which issues do not require deep understanding of the project yet, or very advanced knowledge of steamed assembly, so that you can get familiar step by step. So Stringzilla is probably the fastest string implementation ever on AVX 512, AVX2, ARM. So you can replace the libc standard strings with this, and operations like substring search will become like a couple of times, 3 times faster than libc, 10, 20 times faster than the C++ standard library, by the way. It also adds a lot of like nice features, like it supports ranges. So how many of you have had to split a string by tokens using comma or white spaces delimiter? Raise your hand. And when you do this, you probably have an std vector of std string into which you output, and you have an std string that comes in and you output the vector of substrings. That's bad, because you allocate a lot of
Why
memory.
not vector string views?
That's also bad because you allocate the vector. You still have a vector of string views. Every string view is 16 bytes, 2 pointers.
Small vector of string views.
A small vector would require you to still allocate some memory for like a small vector, maybe a stack. Yeah, but then you have to implement the small vector. Stringzilla has a lot of high-level nice features, like it supports ranges with delimiters. So under the hood, I'm writing synced assembly that will do 20 gigabytes per second, matching substrings, new line tokens, all of those things, whatever you need, different character sets. But on the high level, it supports lazy iterators, so that you can just like take begin of this split operation, and you never allocate memory. You just take the parts that are relevant to you. So this is just like a small promo for Stringzilla for high-level C++ developers, but for low-level fans, everyone knows what memcopy is, right? Raise your hand. Okay, we're doing a lot of exercises today. So memcopy is notorious and well known for like being the most optimized operation in libc, right? If you just take the logs of even CPython interpreter, half of the time CPython is just doing memory copies, not even calling Python code. So the new version of Stringzilla has faster memcopy than libc, which is ridiculous. It's 10% improvement on AVX512, which is pretty nice. Usearch is probably the world's most deployed vector search engine. It runs on all x86 and ARM CPUs. It supports macOS, Linux, Windows, Android, and iOS. It's also powering some of the largest databases in the world. So like when you work with different databases or use unnamed secretive AI companies, under the hood, chances are some of this code is running. ucall is the prototype of the networking stack, and SimSim is the library I was working on mostly today, which is the collection of BLAST-like dot products and similar operations. And this is too much for me. So I'm waiting for all of you to contribute starting today. Thank you. We have 5 minutes for questions, and the mic is over there. Or maybe we can just use raised hands, and if you're a loudspeaker, you may not even need a mic. We have a question over there behind. Oh, you don't need, okay.
So you're saying basically looking at the hardware features, you're calling CppArm maybe thousands of times for one time and just looking at the result. But you said that you're not recommending, or it's not possible to do it in Rust. What's the reason behind it? Because as far as I know, Rust supports inline assembly as well.
There are a few things related to this. So like when I try to write performance-oriented Rust code, it actually ends up being like a lot longer than C++ or C, and almost all of it ends up in unsafe sections. Moreover, like there's some feature detection functionality and nice to have things in Rust, but a lot of this bleeding edge is not supported, or like even outdated things. Like AVX512 has been around since 2015, and it's not supported by the Rust toolchain, at least directly. SVE and SVE2 is so far off that I'm not even trying to like raise this issue with the toolchain maintainers. So with like C and C++, you just have fewer problems you're facing, and most of the ecosystem are like hardware drivers. It's still C. Even with that, even with C99, you'll have so many toolchain issues that using a high-level language with its own toolchain like Rust is just such an easy way to like spend a month only fighting the toolchain. That's my rationale. Oh, one more question here. Yeah.
You want that?
Okay, thank you for the presentation. One question about network acceleration. I heard that it's possible to map socket into a memory, and would you recommend it? That's right.
That sounds like a fun weekend project already, which is pretty cool. I wouldn't do that. Like in general, I avoid memory mapping as much as possible because again, it's not magic. So I'll give you an example. If you build up a database and if you run like a single-threaded benchmark and your database uses memory mapping, you'll see amazing numbers, and then you'll be the first one to post about it and like promote it as the fastest database in the world. So the problem is the benchmark. If you're doing like I/O on one thread and you have a fast SSD and the operating system is just like caching information on one thread, you will not face any problems. But if you have multiple threads accessing the same device and you're working with data sets that are larger than memory, then there will be a background process in Linux. I keep forgetting its name. I think maybe it's like kswap or something like that, which will be like bottlenecking all of your I/O operations, doing swap-like operations, kind of fetching into memory, dumping onto disk, and those operations will be synchronous. Yes, they will be within kernel space, but they will be synchronous. They will be extremely slow, and you'll have hundreds of threads waiting on one single-threaded kernel space process, which means you're losing all of your hardware potential. So avoid memory mapping if you can.
Thanks.
Which fifth row? Yeah.
Yep.
Okay, so do I get it right that the most part of this speed boost we get from this IOU ring is due to the fact that the drivers already are capable to use this, are working asynchronously, while this POSIX, PWrite, and PWread they don't make use of it, right?
Yeah, that's a good observation. Like if you go down, you'll see that most drivers also have ring-like implementation, and they also have like completion queue and submission queue, but that implementation is between like the device and the Linux kernel. But then on top of Linux kernel, if you're doing synchronous calls instead of asynchronous, you're kind of losing all of that. So we now have, in reality, multiple layers of paired rings, and the information is being like taken from one ring, put to the other, and it deepens until the operation is executed on the SSD, and then you kind of pop up the completion result from one queue to another.
Okay, thanks.
Anyone else? First row? Yeah.
Maybe a stupid question, but what happens when submission queue and completion queue will full? Your asynchronous will switch to synchronous execution.
Okay, so we're running a little bit ahead of ourselves, but that's great. So like, I know this person already wants to implement a ring somewhere. You have an operation that submits your submission queue entry into the ring. This operation returns an error code. If the queue is full, the return status code is failure. So the operation was not submitted, and then it's up to you and your application logic to mitigate it. You can create more rings, you can create more buffers, you can wait. The world is yours.
Okay.
I think we've had enough questions for now, and you can catch me after the second talk. And thank you again. I'm inviting Dmitry to the stage for an epic talk about Linux on GPUs. Get excited.
Yeah, thank you everyone. But I suggest taking a 5-minute pause. Would you be all right with that? Okay, 5 minutes while I'm switching notebooks and also just a bit of rest for everyone. Okay?